In this chapter, we will talk about electric potential. Electric potential is different from electric field in that electric potential is a scalar quantity, while electric field or intensity is a vector. And that makes the study of electric potential somewhat easier. So, what is electric potential? We may have heard about this word called voltage. For example, a car battery usually provides 12 volt. Now, volt is the unit of electric potential. Electric potential and potential difference are used interchangeably. So usually when we talk of electric potential, it's always potential difference. We will get those facts as we move along. So as given in this diagram, we have two plates, one positive right there, one charged positive, the other charged negative. Usually how this is done is by connecting these plates to the terminals of a battery. So the positive plate is connected to the positive terminal of the battery, and the negative is connected to the negative terminal of the battery. So that means there is a potential difference between these two plates. And it's easier to remember that whatever plate is positively charged is at a positive potential, and the one that's negatively charged is at a negative potential. Which means that the positively charged plate is at a higher potential. That's why it's positive. And the negatively charged plate is at a lower potential. So when you take these two plates, the potential of A is greater than the potential of B. And potential difference is defined as work done over charge. Let me explain. That means the work that we would have to do to move a positive charge from the negative plate to the positive plate. So imagine that this plus Q charge is initially on the negative plate. And that's where it likes to be. That is the lowest potential energy position. That's like comparing a mass on the ground. All right, so a mass on the ground likes to be there because that's the point of lowest gravitational potential energy. And if you have to lift the mass, we have to do work against the gravitational force. In the same manner, to move the positive charge from the negative plate to the positive plate, we are trying to take it from a lower potential to a higher potential, so we have to do work. When we do work, it gains potential energy. So that's what this delta U stands for. Delta U is the gain or the change in potential energy. So if we know that the change in potential energy is 10 joules, as an example, and if the charge that's being carried is 2 coulombs, then the potential difference between B and A is 10 divided by 2, or rather 10 joules divided by 2 coulombs, which is 5 joule per coulomb, which is also called volt. That means the potential difference between these two plates is 5 volt. All right? So that is the idea of potential difference. Another thing to be noticed is if you have this positive charge on plate A, by itself, it will move to plate B. It's just like if you hold a mass at this point, let go, by itself, it's going to go down. So anything moves from higher potential energy to lower potential energy. So that means for a positive charge, the higher potential energy is on the positive plate and the lower potential energy is on the negative plate. I hope that's clear. what about if you have a negative charge? Which point is the higher potential energy point for the negative charge? Yes, the negative plate is the higher potential energy. Because if you let that negative charge be free, it would move by itself to the positive plate. So remember that higher potential energy for both positive and negative charges are not the same. But the potential is higher for both on plate A. Another way to remember it is this. The electric field shown in this diagram by those red arrows, the electric field always points from higher potential to lower potential. Always from higher to lower potential. So the potential at A is greater than the potential at B, and for a positive charge, potential energy at A is greater than the potential energy at B. But when it comes to a negative charge, again, the potential at A is greater than the potential at B, but the potential energy at B is now greater than the potential energy at A. I hope that makes sense. So now let's get this one more time. The work done is always the negative of the change in potential energy. That means if the external agency does positive work, then the potential energy decreases. Just like saying that when a mass falls because of the gravitational force, the change in potential energy is negative because work is being done by the gravitational force. On the other hand, if you try to lift it up, you're going against the gravitational force. Now, the change in potential energy is positive, but the work done by the external agency is negative. So they're always opposite. So let's apply this to the case of a charged particle in a potential difference. Just like that positive charge kept in a potential difference. Let's say the positive charge is initially on the positive plate, and you know it would move by itself to the negative plate. You remember that? So it starts from initial velocity 0 on the positive plate. So its kinetic energy is 0. But it has potential energy. And so when you let go, its kinetic energy increases because the electron or the charged particle is accelerated. So the kinetic energy increases while the potential energy decreases. Yes, so the conservation of energy holds good. So much so that when the charged particle is about to reach B, its velocity is maximum. So at that point, its potential energy has become 0, while all of its potential energy has changed into kinetic energy. So the thing is, whatever potential energy it had on plate A is now completely changed into kinetic energy on plate B. So can we write this? Q times V, which is charge times voltage, is equal to the kinetic energy. So that was the potential energy on plate A. This is the kinetic energy just before it reaches plate B. Using that formula, we can calculate the velocity of the charged particle accelerated through a certain voltage. So let's say that there is an electron that is accelerated through 100 volt. And let's try to calculate the velocity that it would have on reaching the negative plate. So charge of the electron is 1.6 times 10 to the negative 19 times the voltage is 100, and then half times that is the mass of the electron, velocity squared. When you do that calculation, you get 5.93 times 10 to the 6 meter per second. Wow, that is fast. Also remember that if it's accelerated through voltages higher than 100 volt, then the calculation for velocity will not be correct, since we would have to apply relativistic effects. So the maximum is around 100 volt. So we can, avoid relativistic effects. Remember that. So that is the velocity. And so we also have a new unit of energy called the electron volt. 1 electron volt is the energy acquired by an electron when accelerated through a potential difference of 1 volt. So we can change this into joules by using the conversion. 1 electron volt is charge of the electron times 1, so which will give you 1.6 times 10 to the negative 19 joules. All right? So using the idea of electric potential that we have had this far, let's try to work out this problem. The problem is we need to configure 4 charges as shown in the diagram. So we have 4 microcoulombs, 5, 2, and 3 microcoulombs arranged on the vertices of a square of side 1 centimeter. So question is, how much work is needed to assemble this charge configuration? So the idea is, number 1, remember that electric potential is scalar, is defined as work done. So when we try to bring the first charge, let's say you don't have any charges in that space, we'll try to bring the first one, for example, the 2 microcoulomb, and try to bring it and keep it here. How much work do we have to do? The answer is nothing, 0, because there are no other charges in the vicinity, so we don't have to work against any other force. But when we bring the next charge, for example, the 3 microcoulomb, we will have to do work against the force of repulsion of 2 microcoulombs. So you have the 2 microcoulombs here, you're bringing the 3 microcoulombs, you will have to do work against this charge, right? But when we bring the next one, like the 4 microcoulombs, we will have to now do work against both 2 and 3. And then finally, when we bring 5 microcoulombs, we'll have to do work against all the other 3. So you see how the configuration builds up. Let me show you how this is worked out. So in the first case, as I told you, the work done to bring the 2 microcoulomb is 0, nothing. But when we go to the next one, remember that the formula is KQ by R. So since there are 2 charges, it will be K, Q1, Q2 by R12, where R12 is the distance between 1 and 2, you see. And remember, K is 9 times 10 to the 9, or 8.99 times 10 to the 9, which we round off to 9 times 10 to the 9. And then you have the first charge, 2 microcoulomb. You see the 10 to the negative 6 because we're changing micro into coulombs. And again, 3 microcoulombs divided by the distance between them in meters. And so when we do the calculations, we get 5.4 joules. That's the work done to bring in the 3 microcoulomb. And then to bring the 4 microcoulomb, since we got to do work against both the others, there are 2 terms now. You see that? One is K, Q1, Q3 by R13, and then plus K, Q2, Q3 by R23. All right? So in this case, when you substitute the numbers, we're going to get 15.9 joules. Just remember that this distance between 2 and 4, see that distance is not 1 meter. I mean, it's not 1 centimeter. Instead, it will be square root of 2 centimeters. That's easy to know because this is 1 centimeter. This is 1. So the hypotenuse of that triangle would be square root of 2. So that's why you find square root of 2, which is changed into meter again. Now finally, when you bring the last one, you would have 3 terms now. All right, I'm not going to read out all of that. You will have 3 terms, and the total work done would be 36.5 in bringing that 5 coulombs, microcoulombs, I mean. And so finally, we'll have to add up all the work that we had to do. First one, no work. Second one, 5.4. Next one, 15.9. Next, 36.5. So the total work done is 57.8 joules. Remember that this can be written this way. That's a mathematical representation of the total work done in configuring n charges. You see the 1, 2, up to n would be k by 2. I'm going to explain why k by 2. Sigma I to n, sigma j to n, qi qj by rij. So I and j are the two charges. But remember that we do not consider I and I, no need. So that's why here it says I not equal to j, because there's no need of work in bringing a charge due to itself, right? That's why I is not equal to j. Another thing is, once you have considered the work done to bring 2 and 3, there's no need of taking 3 and 2, because when you take combinations, it'll repeat twice. To avoid that is why we divide by 2 here. So each pair is only considered once, and each one need not be considered with itself. So I hope you. We looked at this setup once, but I just wanted to remind you of another thing. Okay, we already know that the voltage at A is greater than the voltage at B, and for a positive charge, the potential energy at A is greater than the potential energy at B, but for a negative charge, it's the other way around. Potential energy is greater at B than at A. We know that. But if we consider a uniform electric field as shown in the diagram, where the lines are equally separated and parallel except at the extremities, it's a uniform electric field, right? And in a uniform electric field, the strength of the field is simply the ratio of the potential difference between the plates divided by the distance, or the ratio of the potential difference between the plates to the distance. So if we take the potential difference between these two to be some number, we can divide it by the distance to get the voltage. But if it's a non-uniform field, then the standard way of representing voltage is it's the negative of the line integral of the electric field with the distance. In fact, it's the negative of the line integral of the dot product of the electric field with the distance. So that's a dot product between those two vectors. And the negative points that we're always doing work against. Remember I mentioned that. If you can put this in this way. This is integration, but this is differentiation. Same thing, E is negative dV by dL, which is where you get this from. See, you take the difference in voltage divided by the distance, you would get the electric field strength. Now let us find the electric potential due to a point charge. So if we have a point charge somewhere here, this is the point charge, and we want to find the electric potential at a certain distance away from the charge. So let's say at this point. First of all, the definition is, if you're trying to bring a +1 coulomb from infinity up to this point, we will have to do work, right? So let's say this is a positive charge. This is a positive charge, Q coulombs. And we want to find the potential here. So what do? Imagine that you're bringing a +1 coulomb from infinity. As you come closer, wouldn't the force of repulsion on that increase? Yes. That means we'll have to do more and more work. So whatever work we have to do to bring that +1 coulomb all the way from infinity up to that point and situate it there, that work will be the electric potential at that point. So that means it'll be the line integral of the electric field multiplied by the distance, right? So let me write that here. So here it is, the potential due to a point charge. Okay, so that's the point charge plus Q. We're trying to find the potential at this point called P. And so you're bringing a +1 coulomb, and the work done is line integral F dot dr. In this case, F is E, so you can write it as E dot dr. Remember, the limits of integration are from infinity to r. And so when you know that F or E is kq by r squared, right? K, that's Q. Kq by r squared is the formula of electric field. So kq by r squared dr, k is a constant, q is a constant. Take that out, so you have integral 1 by r squared dr. Okay? When you do that, all right, k and q constants taken out, and when you do the integral, you get 1 by r. All right, so 1 by r. So that means the formula for potential due to a point charge is kq by r. Kq by r. Notice the difference. It's not r squared. Don't make that mistake. It's kq divided by r raised to 1. And here I'm writing the definition. Work done in bringing plus 1 coulomb from infinity to the point. Well, we know potential is measured in volts. All right. So that's the formula for electric potential due to a point charge. So let's use this idea to work out a problem. So what you see in the diagram is a Van de Graaff generator. We'll talk about that a little later. But here the question is, what is the excess charge that is built up on the Van de Graaff generator? What is the excess charge? You know, the excess charge depends on the diameter of that sphere. The bigger the sphere, the more the charge it can accumulate. So this one has a diameter of 25 centimeters, and the voltage is 100 kilovolt near its surface, 100 kilovolt. So how much charge is there? So actually, the charges dwell on the outside of this sphere. The charges are all here. But using Gauss's law, we found out that although the charges are situated on the outside of the sphere, we can imagine that all these charges are situated at the center. Therefore, we can take this to be a point charge situated here. If that's the case, we can use what we got just now. Voltage is kq by r. Rearrange that and find q. That's exactly what we are going to do. So the voltage is kq by r, so q is r times voltage by k. Radius is 0.0125 meter. 100 kilovolt is 10 to the 5 volt, and k is 8.99 times 10 to the 9. We get this, which is 1.39 microcoulomb. To always remember that we have used Gauss's law to assume that although the charges are uniformly spread out on the outside of the surface, we considered all of it to be situated at the center of the sphere. Now let's talk about the concept of equipotential surfaces. The name itself shows that we're talking about surfaces that are at the same voltage, equipotential surfaces. So on the left side, we have a point charge, q coulombs, and we know that at the same distance away from that charge, the voltage will be the same, the potential will be the same. So the equipotential surface will have the shape of a sphere. So that's one equipotential surface right there, one there, and then you have another one, and then you have another one, and then you have another one. So all equipotential surfaces are spheres, concentric spheres with the charge at the center. Now, why are they drawn like this? I'm just going to tell you why the space is increasing. Because it's drawn for the same change in potential. What am I saying? I'm saying that the potential at this point is the same as the potential at this point, right? Because it's an equipotential surface. But that does not mean that the potential here is the same as that here. No, they're different. So as you move across the equipotential surfaces, there is a change in the potential. But if we move over the equipotential surface, there is no change in potential. Another interesting thing is that the red arrows represent the electric field. And always, equipotential surfaces are perpendicular to the electric field. Very important. Electric field lines are always perpendicular to an equipotential surface. Sometimes I ask, what's the work required to move a charge from one point to the other on an equipotential surface? That is a trick. The answer is zero. There is no need of doing any work. On the right side, we have the electric field and equipotential surfaces shown for a positive and a negative charge. You can see that the electric field always goes from positive to negative. You can see that there. But these dotted lines are equipotential surfaces. Here again, you have the electric field and equipotential surfaces for two positive charges. Now, both of these are positive. Remember, here one was positive, the other was negative. Did you notice that whatever the case is, the electric field is always perpendicular to the equipotential surface at any point and every point? Now, this one we had considered before, but I just wanted to give you an example. Remember that this is the positive plate and the negative plate, and it sets up a uniform electric field between it. And if you look at it, the negative is always considered to be 0 volt. The negative in practice is ground, and the ground is always taken to be at 0 voltage. So this is the negative, and then you have this. See, this is an equipotential surface. That means the potential all over it. It's not a line, actually, it's a plane. The potential all over it is 25 volt. This one is 50. Here's 75 and here's 100. So you see there is a potential gradient as you move from one point to the other. If you take that potential gradient and divide it by the distance moved, you will get the strength of the electric field. So, for example, if the distance between these plates is 10 centimeter, which is 0.1 meter, when you move from one to the other, the change is 100 volt. So you get 100 minus 0 divided by 0.1 meter, which is 1,000 volt per meter, is the strength of the electric field. Now, usually we put the electric field in newtons per coulomb, but now you have another unit because of this definition, which is volt per meter. Another important concept is that of surface density of charge. The symbol is sigma, and surface density of charge is simply the charge over a surface divided by the surface area. So if you charge a sphere, a conducting sphere, for example, the charge is spread out uniformly all over it. That means if you take any particular area, you will find the same amount of charge. That means the surface density of charge is constant. On the other hand, if you look at a conductor shaped like this, it's very clear that charges accumulate near pointed ends where the curvature is bigger or where it is sharper. The surface density of charge is higher. Okay? This is all right, look at that before I go along. So there you see it's high sigma, and here it is low sigma, so low surface density of charge. A big application of this is the lightning conductor. Lightning conductor has pointed tips on top of high buildings, and then that's connected by means of a cable to the ground. It's grounded. So the idea is when clouds pass overhead, and clouds carry a lot of charge, those clouds induce the opposite charge on the lightning conductor, and because this tip is pointed, there is a huge accumulation of charge there. That means the field becomes really high, and all of those excess charges go to ground. If we did not have the lightning conductor, then the entire building, top of the building, would have got charged, and there would have been electric discharge happening through the building, which would have been very dangerous for the occupants of the building. So now I hope you understand the functioning of a lightning arrestor or a lightning conductor. And then we have the Van de Graaff generator that I talked about a little before. Here, if you look at it carefully, in summary, you can see that there is a pulley made of an insulating material passing over actually there is a belt passing over two pulleys. That's what I meant to say. A belt, and the belt is made of an non-conducting material. And here you have a battery. See, the negative of the battery is always grounded. You see that the negative is grounded. The positive is connected to what is called a metallic comb. So pointed metal tips, because this is positive, this comb becomes positively charged, and as the belt moves, it carries the positive charge way up and gives it to the other comb that's connected to the inside of the sphere. So these charges move to the sphere. In fact, they move to the outside of the sphere because charges always dwell on the outside. So that sphere gets charged. And as this process continues, more and more charge is carried up until finally the charge on that outside becomes so big that the voltage becomes big for the air to become conducting, and you would see a discharge happen. But, before that, we could use that built-up charge, as shown here, for some kind of an electrical experiment. So that is the Van de Graaff generator, and it's working. You can also look at how, a photocopier works. The idea is simply, to have a drum that is charged, and then to have an electrostatic image made on that drum. So it's only those parts that become charged. So if you want to print out the letter A, only that part becomes charged, and then you have charged toner that gets attracted just to those parts, so to that A. And then again, you need to have paper. So paper, and when the paper runs over that toner, it gets attracted to the paper because the paper is charged, and the toner gets deposited, and that's how you get the photocopies. I know I've just summarized it. You need to read on how this works. So that's the photocopier. The other application that I want to talk about is the electrostatic precipitator, where, in factories, if you have a lot of smoke coming out, you could simply avoid the smoke from coming out simply by using a set of grids as shown here. The first one, as the smoke particles pass through the first one charges them. And the second one has the opposite type of charge. So all these charged particles now get attracted to this and then gone. So that's why it's called a precipitator. And then you have the third and the fourth for further filtration. So first, have the smoke particles charged. Second, have them attracted to the oppositely charged grid. There it is. So you do not let them escape into the atmosphere. It's crazy that you would not see any smoke at all in an electrostatic precipitator. So that is this chapter. This is the wonderful chapter of electric potential. That's kind of imaginary. But soon it's all going to make sense when we get to the next chapter, which is capacitors. Remember, all of these chapters together give us one great application, which is the capacitor. So see you on that chapter soon. Thank you.